So we had a lecture last semester about mathematics of the periodic table and the mathematics of quantum physics. Jim Sell, who I see over here, gave a wonderful lecture about astronomy and the Big Bang and how the universe created the elements that we see in the periodic table. And then we have some exciting lectures coming up. So next month will be, it's Takahito next month, right, Maureen?
But before that, we have a new one.
Oh, that's right. We have a new, we added a lecture by David Carter of Los Alamos Laboratory, who is a Nobel laureate, and he'll be talking about plutonium chemistry and the battlefield of the Cold War. And so that should be a really interesting talk about the real impact of plutonium and elements in the periodic table on the history of the world. So I hope you'll come out for that. That's October 15th at 6:30 right here in this room. And then we'll ocean chemistry and global warming and ocean chemistry and different elements in the ocean that whose measurement and whose frequency tell us things about what's happening with our planet. So I'd also like to welcome Dean Susan Lozier, who is the new Dean of the College of Sciences, and she's here tonight, if you could stand up. She's been here for exactly 8 days. And we're delighted to have her here, and I'm sure that Susan would be happy to talk with all of you following this lecture, where we'll have a little reception out in the lobby. We, as always, have a little contest going on, so you will find out the rules afterward, but stay put because 10 lucky people here will win a t-shirt at the end of today's lecture. And you will find out if you're a lucky winner when the lecture is over. And so, last but not least, I want to introduce our speaker for this evening. We have Monica Halka, who is an associate director of the Georgia Tech Honors Program. And Monica has a background in experimental physics and optics, right? Things related to light and atomic
and atoms.
What's that?
And atoms, light and atoms.
Light and atoms, there you go. And she's also written a series of books on the periodic table. So 6 books around 6 different classes of elements in the periodic table. So she is well known for her writing in this area. And so when we planned this lecture series, we thought it would be great to have one of our own Georgia Tech professors who knows so much about the periodic table and has helped popularize it to give a talk, which you'll hear tonight. And in addition to her work with the honors program and her background in physics, Monica also teaches a number of interesting courses for us here at Georgia Tech. And so among the special topics courses she's taught are the urban forest and Harry Potter and the false dichotomy of good and evil. So without further ado, I welcome to you Monica Halka.
Thank you, Matt. I hope you can hear me. Thank you so much for inviting me, Matt and Maureen, and thank you everyone for coming. I see many friendly faces here, which is really nice. So yeah, I don't know how it came to be that I wrote that series of 6 books on the periodic table. That just happened, and I don't know. So anyway, I was invited to give this talk on the elusive end of the periodic table because I know so little about it. So that says as much as I want to say about that. So many heavy elements are found naturally on Earth, and where did they come from? Well, Dr. Sewell talked about where the elements were made in the universe, and as we all know, I think every element up to iron, which as we all know is Fe, which makes total sense, were made in fusion in the centers of stars, right? And then when you get to iron, it can't collapse anymore. It just has to the pressure is just too much and it has to explode in supernovae. So past iron, it's supernovae explosions, except recently there's been a lot of research on some what's going on with some of the heavier elements, and I think some people here are doing research on that. It seems that neutron-star collisions are really responsible for a lot of the rapid process building of these elements. And this paper by Thielemann et al. Says maybe the only source beyond lead and bismuth. And so here, that's not what I meant to do. I meant to use the pointer. So lead and bismuth right here, and it so happens that every element past that is radioactive. Those are all the radioactive elements. There's one up here which is technetium, which is also was radioactive, but I think it's not found anywhere in nature anymore. It's just decayed away and we don't see it anymore. Also, I think, let's see, promethium we may not have anymore. But other than that, all these elements up higher here, radioactive, right? So I'm going to talk about what is found naturally here on Earth. And first of all, where's the natural end of the periodic table, whatever that means. And then after that, go to the very last synthesized end of the periodic table, giving a little details on the way, because if we tried to go all the way from here up to here, it would take a week or so to talk about every element there. So I'll just try to give some details to help you see how these are built. So to think of the natural end of the periodic table, we have to think about how the periodic table was built in the first place. And that was by testing elements for various properties by doing things to them, doing physical things to them, such as heating metal in combination with charcoal, which will give you iron. And then like concentrating urine gave phosphorus, which is coincidentally has the element symbol P, which is appropriate, unlike iron and like Au for gold or Ag for silver, Na for natrium or sodium. So I don't know why we still call it these things. I guess because we don't want to change all the textbooks to all those from all those old names. So, but this was the sort of thing that was done to isolate elements and see what elements there were in the world. And the heaviest element isolated on Earth was uranium. Nowadays, we don't isolate the elements to find new ones, but we synthesize them. Plutonium, for example, in reactors, as you know. However, I just want to talk a little bit about the natural nuclear reactors that existed on Earth and made plutonium in the past. So uranium is not the end of the periodic table on Earth. Plutonium and neptunium have been made on Earth in the past. So to talk about that first, let's see remember what a reactor does. We use reactors to heat water, to make steam, to turn turbines for electricity. And the way that we do that is by using uranium-236. Stop that, I keep trying to point at it, sorry. Uranium-236, which is unstable because of the number of neutrons in the nucleus. And it breaks up into various fission byproducts. Barium and krypton are a couple, that's one way. You can also get a breakup strontium-xenon, and you get a lot of energy coming out of that, some gamma rays and a lot of neutrons, which are useful. And then you're able to get heat out of that and heat up the water. To do this, you need at least 3% uranium-235 in the uranium ore that you're using. But nowadays, uranium ore is 99.3% uranium-238. So you have to do something to the ore that you put in the reactor, and that is you enrich it by putting regular uranium ore in a centrifuge and separating out the uranium-235 and then putting some more of it into that ore, so you've enriched it. And this is what a man-made, a human-made nuclear reactor, how it works. So you got a bunch of neutrons out of that reaction that we got, and the neutrons are really great because then I am going to back up here. See, here you need a neutron right here to interact with uranium-235 to make that uranium-236, right? So you get a bunch of neutrons out of the reaction afterwards, but those are fast, and we need slow, okay? So fast neutrons can't interact enough with uranium-235 to give you uranium-236. So in order to slow down those neutrons, you just put some medium in there that they're going to, collide with and slow them down. And water is one way, one thing that people use. Some people also use molten sodium. It's denser, so it can slow down even more neutrons, right? So there's the moderator in there to slow down the neutrons so that they can then interact with uranium-235. And you also need to get rid of some of the neutrons because even though you slow them down, if you get enough interactions going on in this area, then in this enclosed system here, and you have too much energy, kaboom, right? And that has happened in a couple places, I think. So there are things called control rods that they move in and out of there when it seems like there's too much energy going in there. Those control rods are things that are neutron absorbers, and they can be made out of various things like that. So you didn't expect to get a lesson in building a nuclear reactor, but this is how you do it. It's super simple. Just go home and don't try it. So this is our traditional way that we make it nowadays, although I don't know if Georgia's doing too well with that. However, imagine a different way. 1.7 billion years ago. At that time, standard uranium ore was still about 3% uranium-235. It hadn't decayed out of the uranium ore so much as it has by now. And so, that ore in there, let's say this is all uranium in here, just a cave. This isn't actually, it's probably a smaller cave than this. But in Gabon, West Africa, which is now Gabon, West Africa, 1.7 billion years ago, I don't know what they called it. But, imagine this is uranium ore. And you've got a lot of uranium-235 in there. And you've got some slow neutrons. Where would the slow neutrons come from? That's a question. Turns out uranium-238 sometimes breaks up by fission, and you could get neutrons out of that. So if there was that kind of situation, if you have enough of it, and you have some water here, right? So you've got the neutrons being ejected and slowed down in the water, enough so that they can interact with the uranium-235 that is coming out of the rock at 3% also, and make uranium-236, and then get fission. And this is an open system, however, right? You don't need that control rod to stop it. So what happened in those places most likely was that once you got a lot of heat going in there, the water would evaporate, and you just have steam, right? And steam is not dense enough to slow down the neutrons. So for a while, the reactions would quit because the steam was there and it wasn't water. And then the steam would condense back down into water, and for a period of time they can actually measure from the geology of it that, for a certain amount of time, you would have the reactions, and they would shut back down with the steam, and then you'd have the reactions again. As I said, in Gabon, West Africa, there are at least 15 known sites, but they're probably all over the place, right? Colorado has big uranium ore deposits, right? You would just have to go in and test how much uranium-235 is in the ore in that place. And that's how they knew something was wrong here. There was too little uranium-235 in this ore. It should be standard across the board, right? So also anomalies in local isotopes here, like ruthenium and neodymium, indicate historic presence of decay of uranium-236. So in this situation, we had uranium-236 becoming fission byproducts and making heat, making this nuclear reactor, but also these slow neutrons here here that would come out could also interact with all that uranium-238 that is there, 97% uranium-238 that was there. And so in that case, 1.7 billion years ago, then uranium-238 could become uranium-239 with a slow neutron in there. And then you get these decays here. And you see these are pretty quick decays. And you get neptunium. This one, not that quick, 24,000 years. But if it was happening 1.7 billion years ago, 24,000 years isn't very long, so we don't see this. All we see is the byproducts, right? So when I was writing those books and I discovered this, I thought it was just so interesting. I wanted to show it to you. Now, you actually could, in uranium deposits, occasionally get this happening because you could occasionally have a slow neutron coming by from somewhere and interacting with uranium-238, but it would be such minuscule amounts you would never see those atoms. So I maintain that neptunium and plutonium are the biggest naturally made elements on Earth, even though we don't still see them around. Okay, so let's go on. We've indicated that. Here we talked about how neptunium and plutonium was made. I'm just going to go this far up to show you how these are made, because these three, curium, berkelium, and californium, are super important for how we got these up here. They're needed in the reaction. So we have to see how we get these, because they're not naturally made, right? And let's just point out again here that you know, we have to make them, but again, they're all radioactive, right? So that means they don't stick around. So you can't just make them and save them, right? They just do whatever they want. So, okay. Sorry, this is just, but I circled the things you need to know. Right. All right, you already see how we got these things. Neptunium decaying to plutonium, you saw that. Then plutonium, you can add a slow neutron there. Get different isotopes of plutonium here. And when you finally get 241 plutonium, then it decays by beta decay, which is an electron coming off. That's an archaic term, beta decay, that still exists. And we get americium, which is the next element in the periodic table. And then you can keep going with plutonium, and you can get an isotope of plutonium with slow neutron attachment. And when you get to plutonium-243, beta decay again like this, then you get another americium, which is not 241 isotope, it's 243 isotope. You need that to get down this chain here. Decays to that isotope decays to, by beta decay, to curium. And curium is one that is going to be needed in one of those very heavy element synthesis. Here we have curium again, a different isotope, right? It's 244, but then you get curium-242 and similar processes with neutrons and decays. And this is, as you know, a helium nucleus that we don't call, of course we don't call it a helium nucleus. Too easy. This is an alpha particle. Sometimes it's a helium nucleus. They didn't know what it was when they first discovered it, right? The alpha particle, and the electron's a beta particle. So yeah. So sometimes you'll see this as an alpha, right? But we just put it here so you can count things up there. I made this equation myself in Word, and it's really kind of weird. I don't know what happened there. But so this is how you get californium, with curium and helium nucleus. And you get a neutron coming off of that interaction. This has a quick half-life, this californium. And then, but the one that is most often used is californium-252 isotope, which you get by more iterations of neutrons and decays. Again, we can start with americium and an alpha particle or helium nucleus, and we get berkelium, which is another atom that is needed to make those final elements. This one, berkelium-243, has a short half-life. The one they'll be talking about, the isotope that is used in the other collisions has a little longer half-life, but those are just different iterations of the same atom. And you get other isotopes of these similarly or from decay processes. So I just want to point out that, again, looking at problems with this scheme of making heavier elements is that, for example, the two isotopes that are used most in these collisions right now, CF252, this is a truncated decay chain that just tells you a few things that happen here. And you get curium. The californium-252 lives 2.6 years, okay? Annum years. But down here, the decay product, curium-248, lives 348,000 years, right? So we've made, by making californium-252, we've made a radioactive element that lives for 348,000 years, right? Something that didn't exist in the universe before that is now radioactive for 348,000 years. So, and this is true for every element that we synthesize. We're making more radioactive elements, right? And for berkelium, here's a decay chain. I just can't find similar decay chains on, the web. But you can see how many elements here are radioactive coming down this decay chain. Radon, yeah. So that's just a reminder. That's just a reminder of one issue with making these elements. So we've seen how those are made. And now we're going to go here. I'll just tell you that to go from californium up here, you can be using some neutrons for slow neutrons in here. But then after you get up here, it kind of doesn't work. They had to go to smashing two heavy atoms together, like beams coming together. And that takes a lot of energy to move heavy ions. So, but that worked here, and they got up around here somewhere, and that wasn't working so well anymore. So then they started using stationary target again, and a little bit heavier beam than like neutrons or alpha particles. So I'm going to just say that these were made in slightly different manner, but not go into each one of them, because we're really pushing the envelope here, right? This is what we're thinking about. So last decade-ish is when these last few ones were made. So here's how you synthesize. See, I've made it very simple right here. Synthesize, I can say that. So you're smashing different nuclei together. It turns out that calcium-48 ion beam is readily available. Dubna has one, and I think Livermore might have one. So calcium-48 is, they purposely, because they did some calculations that if we are able to use that on different ones of these targets, we might get the elements that are heavier. So nihonium, right there, that's a zinc beam on bismuth. I've got a little star right there, which we'll talk about in a minute. What do you think that is? Fluoridium? No. Fluorovium. Some guy. So this is calcium-48 on plutonium-244 target. So a radioactive target that has to be shipped to this place, and half-lives and things. Moscovium, I had to look. Moscovium-115. This is the decay product of 117 down here. These were not discovered in order, okay? Quite often, if you've seen Mendeleev's table, they weren't discovered in order, right? You're just trying to see that doesn't fit right in there. We see what the decay products are, what have we got. So they got 117 before they got 115. And 115 was a decay product of 117. Turns out, nihonium is actually also a decay product of 117. So if they got 117 first, they wouldn't have had to do that. Right. Livermorium, you can see where these names are starting to come from here. Lawrence Livermore National Lab. Again, calcium-48. This is on curium. Remember we saw the curium, where you make curium. Tennessee, after Oak Ridge National Lab. They didn't make it there, but I'll show you why they got their name on there in a minute. And Oganesson, named after Oganessian, who is at Dubna. I'm not going to talk about all the competition and arguments about what the name should be. And I think Sam Keene talked about that a bit. So this was calcium-48 on a californium target, which we talked about that. I'd like to go and see if we can watch this 1.5-minute video from the people at Oak Ridge National Lab, so you can see their feeling about what they had done and why it was named after Tennessee. We'll see if we can get it here. Oh, no, we can't get it. Oh, there we go. Maybe it's going. Yeah. There we go. Let's make it big. I can't do it from the monitor.
The discovery of new elements is actually very exciting on a number of different levels. And what we have done with our partners is we have changed the periodic table, and we have changed every high school chemistry book.
You what?
Now, from a scientific point of view, what we have done is we have extended the periodic table to new nuclei, which have more neutrons and more protons. These extreme nuclei are very sensitive tests of our understanding of nuclear physics. The project began at the high flux isotope reactor with the 6-month irradiation. The products of that irradiation were purified at the Radiochemical Engineering Development Center at Oak Ridge in a 3-month campaign. The output of that was 22 milligrams of berkelium-249.
22
It's a
milligrams.
synthetic element. It's not one that exists in nature. That material was shipped to Russia. It has a 300-day lifetime, so we had a very short time to do the experiment. They irradiated with calcium-48 ions, and in that process we created only 6 atoms of element 117. And it's the result of the International Union of Pure and Applied Chemistry reviewing the published results of our experiments and follow-on experiment that led to the assignment of priority for element 117 and 115, which is a decay product of 117, to Oak Ridge National Laboratories and our partners at Livermore and at the Joint Institute for Nuclear Research in Russia.
So he sounded most excited about that textbook thing to me. How ironic.
Can I ask a question?
Yes, if I...
Being from Tennessee, they're in Tennessee, and the abbreviation for Tennessee is TS. How did they end up with TS?
That's a good question. Maybe is. Yeah, I don't know. This now I can't close this. There we go. Yeah. Well, I didn't name it. Okay. Okay, so where they get these targets, I've already told you that was 22 milligrams of berkelium-249 that they had to transport. I don't think they put that on Delta, do you? They had to make it travel pretty fast, right? They only had 300 days. Let's see what else it takes to make these things. You need to transport you need to get the target material, berkelium. So they had to wait to get the berkelium. They had to ship it there, and they had to have everything ready. Let's see what else you need. A lot of times they had 22 milligrams of the berkelium, and so they. That was for 117. This for 118. It was 1,080 hours. That's a month and a half, okay? A month and a half. And a lot of my work was done at accelerators. They usually go 24 hours a day. Everybody pulls shifts, right? So, and made 3 nuclei for element number 118 people. Lots of money. I want to talk about this. Calcium-48, that's the standard beam material, right? That's $250,000 a gram, okay? plutonium as one of the targets, you can look this up. You can look these things up. The cost, it's like Bloomberg. $185 a milligram. Well, that doesn't seem too much, except a milligram is 1,000 times smaller than a gram, so I mean 100,000, I can do the math, right? I'm just quoting their prices. I couldn't find a price for plutonium-240. They got it somehow, probably from one of their Russian reactors, right? That might not have cost them anything. Berkelium-249, $185 a microgram. So this is 1,000 times less amount of material. So microgram is, what did they use? 22 milligrams, he said? But guess what? They didn't have to pay for it. They had to wait and wait. It turned out with that crop of berkelium that they made was a byproduct of californium, which they were making for a company. Companies buy californium. I'll tell you why companies buy californium. It's a source of neutrons. It's one of the few good sources of neutrons, and it's used as portable neutron source for detection of gold or silver by on-the-spot activation analysis, and moisture gauges for the determination of water and oil-bearing layers in oil wells. So californium is, even at the cost of californium, that's big M is a million. Only I read from some guy that was buying it that you never can buy a gram. It's not made in that much. A milligram's about what you can get. So it's really $27 million a milligram. But companies pay for it because it's so useful as a neutron source. So they made, Oak Ridge was making californium for this company, and the guys in Dubna were just waiting. And berkelium was a decay product of californium-252, so they saved that for those guys, and that's how they got it. They didn't have to pay for the berkelium in that case. It's nice to have friends. Yeah. Yeah. So that's pretty spendy. Then, like I said, airfare for your radioactive targets. Then accelerators. Here, let's talk about this. I didn't know about this till I was forced to give this talk, which is coming online. She forced me. Coming online in 2022 at Michigan State University. Who knew? Heavy ion facility to look for element 119, which, well, see, 2022, and the cost is, they said $730 million, but my guess is the estimate's always a little low, right? Dubna is already looking. That's the Joint Institute for Nuclear Research, the Russian place called JINR. And they're looking right now this year, and they're saying it will cost them about $60 million to find that element. So that's, I don't know. Then Japan, Nihonium, by the way, is named for Japan. They have a big facility there. They claim that the cost to search for element 119 for them is only $1 million a year. But it's hard for me to believe that would cover the salaries of all the people that are working there, right? I don't think that that's right. So this is a very, 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 very expensive business. And a lot of energy is used. I could not find the specs. I looked at the annual report for JINR and other places. They don't want to tell you how much energy they're using. You can find out how much energy is in the beam, but I'm talking about the whole facility. I was able to find for the Large Hadron Collider, which, they are accelerating really lightweight particles, so I think they might be using less energy than the heavy ion facilities. And so they use about 1.3 terawatt hours of power per year, which a trillion watt hours. An average household in the US, about 10 megawatt hours per year. So if you do the math, quite easy, it's enough to power 130,000 households in the United States. If it's in Europe, about a third more, because Europeans use about 6 megawatt hours per year on an average household. So this is a lot of energy, which is also a lot of carbon put into the atmosphere, I would say. And that's a problem. It's getting to be a problem. It wasn't when they were first working on these things, right? So the question is, why? For God's sake, why? we need to go back to understand why the periodic table even started in the first place. It's because the human need to categorize things. This is how we learn, right? Everything we learn, that's how we learn. We categorize. We start when we're children categorizing things. And, you know, early on, element classification, I mean, I don't think we can help it. There's a problem. I mean, we have problems of racism and not wanting to accept people at the border because we're categorizing, but I'm not sure we can help it. I think we should be aware that there's something in our heads that makes us do that, but there is, right? So early on, it was about macroscopic behavior. Things like they were measuring, okay, we'll classify these elements by melting point. Then do they go in the same column? Or reactivity with other elements. Then do they go in the same column? Hardness, color, room temperature, state, liquid, gas, solid, whatever, right? So that was how it started, because no one knew what was going on with those elements. Now we know that the behavior is related to the combination of electrons in the outer shell of the atom, right? Because it's the outer shell electrons that are causing the reactivity with the other atoms around them. They're interacting with them. And the reason for that, for all this categorization, is we think if we can categorize things, then we can predict things, right? So how many sticks do I have? Oh, not enough for the winter. I'm going to go and grab some more sticks, right? So we think that this table that we got is helping us to predict things and predict behavior and tell us what's going to happen, because we don't like the unknown future. Unfortunately, then my question is, why is this such a big mess? I mean, the whole idea is that the columns are alike, right? Well, let's just look at the first column. One of these things is not like the other. One of these doesn't belong. But I don't know. What's that doing over there? This is a non-metal. These are alkali metals, and that it just doesn't fit there. It doesn't behave like they do, but it's over there. Yeah. It's got one proton, that's why. And then we go all the way over here to 2 protons. We've got helium. Well, this is behaving very nicely. This is behaving very nicely. Let's see, the alkaline earths are behaving very nicely here. This is a big conglomerate that they had to spread out into a whole bunch of rows, including these. These belong in here. They're sticking out this way, because they just didn't have any place to put them in here. The problem is they all behave the same. Well, that doesn't make any sense. Don't we have more electrons in each shell as we go to the next column? No, we don't. Problem is we don't know what the electrons are doing. What happens in these is that you have an inner shell that doesn't fill completely before another outer shell starts filling. So then, when you get more protons and electrons, they start filling the inner shell before they fill the outer shell, so the outer shells are just staying the same, and all the behavior is kind of acting the same with interaction. So that's that's just a gigantic mess thing. Then we've got, I don't know, people saying, why can't we have silicon-based life? We've got carbon-based life. It's right above it in the periodic table. It ought to work. Well, silicon is a semi-metal, band gaps and all this stuff that we use in solid-state physics, and carbon is a non-metal. They're not alike, right? So these predictions are not working. Down here I said these seem to behave okay, but I can't tell you if those behave okay, because none of these things that we make have any electrons on them. They're just making nuclei, right? That's not actually making atoms. They don't live long enough to make an atom. So it looks like they belong there, but so we think we can predict, and we can't predict. Why can't we predict? The problem is, well, I heard one of the talks where the person said that inside the atom, the electrons are repelling each other, so we don't know what's going on. But that's incorrect. We have no idea what the electrons in the atoms are doing, but I can tell you for absolutely certain that there is a case There are many cases where the electrons are attracted to each other inside the atom. This was my thesis work for my PhD at Los Alamos National Lab. And we were working with a relativistic negative hydrogen beam. So hydrogen's very nice. It would be just these two things here balancing each other out. And you can put another electron in there. Does that surprise you? It surprises a lot of people, because if you only take into account the Coulomb force, electrons repel, light opposites attract, then you try to put that electron on there and it's not going to stick. Odd thing though, you put that electron on there and that negative hydrogen ion is absolutely stable, never decays. It's absolutely stable. So that's weird, right? And so that just shows that they're not repelling each other the way that you think they are inside the atom. We can't really look in there. But the experiment that we did was to shoot a laser beam at the atom and vary the energy of the laser beam and see how the electrons come off the hydrogen ion beam. I'm telling you this just to show you how we don't know what's going on with the electrons and how we can't know. So here's the one experiment that we did. Now, the first detachment energy for hydrogen is up here, like at 13.6. For negative hydrogen, down here around 13.5 electron volts. The red line is what you would expect if you just had one electron coming off at a time as you increase the laser energy. At first, a whole bunch of them would come off. And then you would get a slight rise, after you've removed a lot of the electrons. Yeah, that's what it should be, but what the heck is that? What is that right there is electrons refusing to come out of the beam, right? As these energies here. And it's a whole series. These are, the resolution of these, the width is not that good. There's a big series here. These are resonances where the electrons are hanging on to each other for dear life and not leaving the atom. So this is an electron attraction. How can that be? It's a wave function overlap. They're so close together, the wave functions are overlapping, and they think they have the same wave function. So they're just existing as one particle, essentially within the atom. And the spectra get much more complicated. Like for helium, helium does this too. Negative chlorine that we've done. Barium, we've done many different, we call 2-electron atoms the ones with 2 electrons on the outside. So the electrons are not behaving the way that we in our minds think they should be behaving. And I think that's why we have all that weird, strange mess in the periodic table, because we think the outer shell is the only thing that matters, and we've got a lot of weird correlation that is going on with wave functions, not individual particles like planets, as we know. So I got to stick in something about wasn't that clever how I did that? But electrons don't matter for the heaviest elements, so why the heck am I talking about that? Electron shells and all that. The heaviest elements are just nuclei, right? So what are we looking for there? Oh, I see. We're looking for nucleons that are arranged into complete shells within the atomic nucleus, as if we knew what they were doing. The premise is that if you have a certain number of neutrons, a certain number of protons in an atom, that some of them should be more stable than others, right? And not want to break apart and decay and have very short lifetimes like those other ones have. And they call those magic numbers. And we reach an island of stability that looks exactly like this. And we take this road. So atomic nuclei consisting of such a magic number of nucleons would supposedly have a higher average binding energy per nucleon, supposedly. And so here's a prediction for hassium, one of the higher ones, 108, and fluorovium, okay? That they should be islands of stability because of their nucleon number, their magic number. Let's check. Oh, let's see. Okay, here's the lifetimes, half-lives here. Here's the element number, 108, 114. Well, I don't know. What does this look like? Here's one that's 10 minutes. That's pretty long-lived, element 104. We go down, 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 down. 11.4 minutes. Compared to those others, that's kind of long. There's an isotope there that lives 11.4 minutes. However, 114 should be really stable. That's one that was really expected to be an island of stability 5 seconds and 21 seconds being the maximum half-lives of these two. And then you go down, you keep going, milliseconds, microseconds, milliseconds, 1 millisecond, okay? I don't know about you, but I'm not seeing a lot of stability down there as predicted. You know, I guess it would be really cool if they were, you know, if there was some place, maybe it has to be a lot heavier. I don't know, maybe they can. And I guess that would be cool. But I'm trying to understand why this is being kept up at such expense, right? And so here's what I'm told. This was from a paper and quoted Oganesson. It's the biggest prize out there, one that could revolutionize energy, or guess what, change the face of warfare. What do you think about that? You believe that? Revolutionize energy. So what does that mean? Like we would have some kind of new nuclear reactor using these really heavy elements that are really hard to make. We can only make a few at a time. Well, if they lived a long time, maybe you could collect them and do something with them. But I mean, it's hard to get nuclear reactors kind of going with energy now. That would be pretty expensive. So I don't know. Changing the face of warfare? I don't know very much about warfare. I mean, I think thermonuclear bombs are probably pretty good at warfare. I mean, my father worked on those for several years in Enuitak and Bikini. Bless his heart, as they say here in the South. But I'm, you know, I don't know what to think about this idea of changing the face of warfare. I suspect that that is the selling point to the governments, especially in Russia, right, where they're working so hard to get these heavier elements. And so, you know, I suspect that's it, but you know, mostly it's competition because we saw all those, just competition to get your name, it seems like to me in the textbooks, because we saw that Japan is working on 119, you know, the New Michigan place is working on 119, Dublin is working on 119. So everybody's working on this at very, very high expense, and I'm not sure, you know, what the benefit is. You'll have to decide for yourselves. For the students here in the room, I think maybe I would like to tell you that I hope you really love science and you'll keep loving it and being interested in it as much as I am. But hopefully, maybe ask some questions, you know, about what's going on here, about the culture of science. What are we doing? How are we doing it? Who is funding it? Who is it benefiting? Who is it hurting? Right? And looking at all these new experiments are very exciting, right? But what are they producing and what could they be doing better? And one might actually think to use all this money on ideas for carbon sequestration or some other health benefits or environmental benefits might be put to better use. So thank you.
Do we have questions for our speaker?
Is there a non-metal other than carbon that...
Not in that column. Not in that column. There's nonmetals in the next column over.
that could be a basis for life?
Yeah, I see what you're.
Silica is not appropriate.
Yeah, I see what you're getting
Is there
at here. Let me
anything
see if I can get back to a periodic table here. See, we've got carbon there. We've got these other nonmetals, but they don't behave in the same way with the same electrons in the outer shell situation. So it seems like carbon, oh look, I have this whole thing. Carbon is the only nonmetal sitting in this row by itself. So it seems like, you know, carbon's a solid, nitrogen's a gas, oxygen's a gas, phosphorus powder or something, you know. So I don't think so.
You mentioned like adding a row to
Can you use the microphone?
the element.
Is that on?
You mentioned like adding a row to the element. Is there any theory? Can we add another row, and another row, and another row? Is there any theoretical maximum for physics or
These guys,
whatever?
Oganessian and the people that are working on it, don't believe that there's a maximum except for the amount of energy that we can make for the colliders. So it is interesting. They're bragging they filled out this row. That's nice. I think it's nice. But they are trying to start a new row and keep going. There's some magic number that goes, they're saying we have to wait till we get to element 176 or something like that. I'm like, well, that's
Well,
going
what
to be.
happened to 176?
Oh, we're going to have another island of stability, just like we had at, well, the idea is that would be really stable. But they've been wrong about that before.
Oh, okay.
So,
Yeah.
no, I
One.
don't know. Yeah. Kai.
Related question, in light of what you consider the weird, strange layout of the table, in light of what you consider the weird strangeness of the table, we were talking about 119 and 120. How would they adjust that to be consistent with what we know everything else to be?
They would have to, now these go in here. They just take these two whole rows and smash them in there, right? They would start over here again. But they wouldn't be able to check if the electron behavior, because they only get nuclei that live so short that they wouldn't be able to check the behavior. So they just start adding protons, and the decay product tells them if they've got that number 119, and they would just go down to the next row because they have a whole lot of faith that this is a proper organization. When Sam Keen was here, he showed all these like three-dimensional models and stuff of what people are trying to make new periodic table orientation. And the reason for that is that this is just weird. It was pretty good for Mendeleev, but it's getting, it's not predicting anything, right?
Are there any possible routes to more efficient synthesis of this? Because it's also sort of an academic issue. You can't test the electronic properties to see if they're actually behaving chemically like you would expect. Is there any way to scale up production from 3 nuclei to something more meaningful?
Well, there is some speculation that maybe these some heavier elements are made in stars, right? So if there would be some way that you could get closer, it's just that they decay so fast that you can't see them. And there's an awful lot of energy and, more than we've got in stars. And so they may be being made there. So maybe some better detection in that area might work. But other than that, we're just using a ridiculous amount of energy trying to make these,
Is there any kind of modeling being done in regards to specific proton or neutron structures within the nuclei in the search for stability?
Yes, the theorists are working on it all the time, and in particular, these guys that work at DUBNA. You saw the guy from Tennessee, from Oak Ridge National Lab, says these are a good test of our understanding of nuclear structure, because they're trying to decide what decay products should I see. Do we understand the nuclei, these heavy nuclei, what decay products are we going to get? And that's how they're deciding if they've really got the element that they think they got. So they are working on these, like with these magic numbers and trying to figure it out, but it's tough going, it seems like.
And kind of play off that, are there any kind of geometric trends that you've seen in the internuclear space?
Not me. I'm not a nuclear physicist, actually. I'm an atomic physicist, so that's not my alleyway. But there are people working on it, which you can certainly find their work. Jim has a question. Now I'm
In our understanding
scared.
of strong force, is there a theoretical volume or diameter that the largest nucleus could be?
Given my understanding of the strong force, I don't know. I'm not knowledgeable enough with in this regard the strong force. Sorry.
Any other questions? Okay, well, let's thank Monica Halka.
Thank you.